Now, the reason that I wanted to wait to start slide 35 is that the next topic that we're going to discuss about acids and bases can be a little bit tricky. So I wanted to make sure that I covered all of that in the same lecture. Okay? Now, our next topic is going to be acid-base properties of salts. So salts are going to be ionic compounds usually formed by a metal and a nonmetal. So for example, something like sodium chloride or HCl, all right, where we're sort of loosely defining metals as everything to the left of that squiggly red line on your periodic table, and everything to the right is your nonmetals. So you're going to have something from the left and something formed from elements on the right of that line. Okay? Now, everything to the left is probably going to be a cation, so you're usually going to have something like a metal cation, which is going to be positively charged, and then everything to the right, your anion will be made up of nonmetals primarily. Okay, now to determine if a salt is acidic or basic, we're going to look at those two cations, or we're going to look at those two ions, the cation and the anion, in the salt. Okay, now going on to slide 36, we're going to have two different types of anions. The first type are going to be anions that act like a weak base, and those are going to act like a weak base if they pull H plus out of solution. And that should sort of make sense. If we pull H plus out of solution, then that means that we are going to raise our pH. Okay, we're going to lower our concentration of H plus, which raises our pH. Right now, this would be, for example, if an anion is the conjugate base of a weak acid. Okay, so in order for us to be able to pull out our H plus, we're going to have to be our conjugate base of a weak acid. So for example, fluoride minus is an anion that is a conjugate base of hydrofluoric acid, which is a weak acid. Okay, so for example, F minus can pull H plus from solution to form an equilibrium with HF. Okay, so even if we didn't have H plus as something that was in the solution, right? We also know that water contains hydrogen, so we'd be pulling out a proton from our water and thereby producing HF. And so let's say that we did it this way, right? Where if we didn't have any H plus in solution, right, one source of a proton is water. So if we were to add water, or if we were to add a salt into water that had fluoride ion that dissociates, what would happen is we would form HF by pulling off one of our protons from that to get OH minus, which is why it will end up acting like a weak base because you're actually producing OH minus in the process. Okay, so since HF forms an equilibrium and is weak, that makes our F minus a base because it's going to be pulling out that H plus. Okay. In other words, if I added sodium fluoride, right, sodium fluoride is going to completely dissociate, and I'm going to be adding fluoride minus, right? So since I'm adding fluoride minus in that salt, it's going to be a basic salt because it's going to lower my pH by pulling out, or it's going to lower my concentration of H plus by pulling out some of that hydrogen from the water. Okay? The second type of anion is going to be pH neutral. Okay? And it's going to be pH neutral if it completely dissociates from H plus. Okay? So for example, if an anion is the conjugate base of a strong acid, an example of that would be the chloride ion. So chloride is the conjugate base of hydrochloric acid, which is a strong acid. So for instance, if I added hydrochloric acid, right, it completely dissociates into H plus and chloride minus. So if I put chloride minus into solution as part of like sodium chloride, it's just going to completely dissociate with any H plus that's in the solution. So it's not going to pull it out. Okay? So since the HCl completely dissociates, no equilibrium forms. Okay? And that means that no H plus is going to be pulled out of our solution and our pH won't change. Okay? So let's do an example of how we might solve one of these anion type problems. Okay? First thing that you do, let's say that we have lithium nitrate as our salt that we're going to add. All right? First, what we're going to do is we're going to separate our species into ions. Okay? So we're going to have lithium plus and our nitrate ion. Okay? Then we're going to add H plus to the anion. Well, we know that our anion is our negatively charged species, so we're going to add H plus to our nitrate ion. Okay? And that's going to give us HNO3. Then you're going to look at that species that you formed, and if that acid that you formed is strong, then it's going to be pH neutral for our salt. And if the acid is weak, then the anion is going to be basic. So, is nitric acid a strong or a weak acid? It is a strong acid. So that means that our salt is pH neutral, all right? Or that we'd rather have a pH neutral anion, okay? The next thing that I want to do, let's do another example, all right, is let's say that we add sodium acetate into solution, all right? Our steps for that, the very first one is to separate our species into ions. Well, we know that we're going to have sodium plus and our acetate ion. So we have C2H3O2 minus, okay? Our second step is to add H plus to the anion. That's our anion. So we have HC2H3O2, all right? And our third step is to take a look at that acid and say, is it strong or weak? Okay, well, that's acetic acid. And we know that acetic acid is a weak acid. And since it's weak, that means that it must be a basic anion. Okay? So I know that was a lot of definitions, but when you're actually working through the problem, it's not so bad. All right? Let's do one more of these examples on slide 37. Okay? So example C would be, let's say that we have Nh4 Cl. Okay, so ammonium chloride. Right? Our very first step is going to be to separate into ions. So we have our ammonium ion, which is Nh4 plus, and we have our Cl minus. Okay? Now, we are going to, and actually before I do that, let's see. Before I do that one, we should probably cover, so if we're just looking at our anion, right? If we look at our anion, we know that we're going to add H to that, okay? We'll talk about how we do our cation in a minute. Our anion, we added H to that, so we have HCl as our acid. And then we want to know, is HCl a strong or a weak acid? Well, HCl is strong, right? Be sure that you guys have memorized whether or not which acids are weak or strong, okay? Now, it is a strong acid, which means it's going to completely dissociate. Okay? And since it completely dissociates, that means that it is going to be a pH neutral anion. Okay? Now, in order for us to figure out whether our salt is acidic or basic, we're going to need to look at both the anion and the cation. Okay? But we know that at least our anion is pH neutral. Okay? Now, before we talk about cations, I want to do one more sort of problem-based example of something you might see on a quiz or an exam. All right? And that's on slide 38. Right? And for this, we want to try to determine the pH of a solution containing the anion. Right? This would be like our conjugate base. Okay? So, here, the process is the same as calculating the pH of a weak base, right? So we did those weak base calculations, right? We had the strong ones where they completely dissociated. We had a weak base problem, which involved an ice table. and an equilibrium, right? So if we're dealing with a weak substance, it's going to require an ice table, okay? But the main difference is that we must convert our acid dissociation constant into a base dissociation constant. Okay, so let's work through the example. All right, the first question that we're going to ask ourselves, I'm working through the example on slide 38. Okay, and that example is, write that out a little bit, that way you guys have all the details. It wants us to find the pH of a 0.250 molar sodium acetate solution. Now, the Ka for acetic acid is 1.8 times 10 to the negative fifth. All right? Now, our very first question is that we need to ask, is it a weak acid or a weak base? And the answer is, we know that sodium acetate is going to, right, this was our acetate ion, right? We did that whole process, and we said that this was going to act like a weak base, right? So the answer is yes. That means that we are going to use an ice table, right? So setting up our ice table, we have C2H3O2 minus plus H2O, okay? We're going to take our ion and we're going to add H2O because we don't have any H plus in solution, right? Because all we've done is we've added sodium acetate into solution, okay? So we've mixed this with water, okay? So we know that that's going to form an equilibrium because the acetate ion is our conjugate base of the weak acid, acetic acid. All right, so this is going to pull H plus out of solution. So we're going to have H, C2H3O2, and we're going to produce OH minus in the process because we've pulled off one of our H's from the water. All right. Now we're going to set up our ice table, okay? And in our ice table, are we going to include our water? And the answer is no, right? Water's not going to be participating in our ice table. We have our initial concentration of the acetate because it's 1 to 1, all right? So 0.250 molar. We started out with none of these. Okay, then we have 1 times negative x, 1 times positive x, and 1 times positive x. We add them up, we get 0.25 minus x. We have x and x. Okay, now, as I mentioned, right, we didn't add acetic acid. We added sodium acetate. So we're adding our conjugate base to solution, okay? So since we're adding our conjugate base to solution, we actually need our Kb reaction, okay? Which this is our Kb reaction, right? We've taken this as our base, and we've added our H plus, and by taking it from the water, okay? So since this is a base reaction, right? It's the reverse of a dissociation, okay? So that means that we need Kb for the base reaction. All right. So step 2 is going to be, is the salt, right, anion gaining an H plus, right? So you're going to ask yourself, does this gain an H plus? And the answer is yes. Okay? And if it's yes, then what you have to do is you need to convert Ka into KB, right? Well, we know that Ka times Kb is equal to Kw. We know our Ka and we know Kw. So we've used algebra to get Kb, which is equal to Kw divided by Ka. All right, so I know that this is 1.0 times 10 to the negative 14, and I'm going to divide that by my Ka, which was 1.8 times 10 to the negative 5th. Okay, so that gives me a Kb equal to 5.56 times 10 to the negative 10th for my acetic acid. Okay, now that means that once I've got my Kb, I can use my basic ice table. Okay, so all the ones we've seen so far have been acidic. This is a basic ice table because we're adding our proton to our base. All right, now I can say that Kb is equal to my expression here, which is going to be x squared over my 0.25 minus x. Okay, and I'm going to say that that's equal to 5.56 times 10 to the negative 10th, because that's what we found for our Kb. All right. And that's going to be step 3, right, which is going to be to build our expression. Build your Kb expression, right? And we did that by taking our products divided by our reactants, okay? And now this is going to allow me to get x is equal to 1.17 times 10 to the negative 5th. Since this is a basic table, right, I'm going to solve for my equilibrium concentration of OH minus, right? So I'm looking at my OH minus concentration at equilibrium, so I know that's equal to X, which is equal to 1.17 times 10 to the negative 5th, right? Because we just found what X was. Okay, then we're going to calculate our POH, again, because we're dealing with a basic table, all right, which is going to be the negative log of my concentration of OH minus. Okay, so I just plug that number into my log, and I get 4.93 as my POH, right? Our last step is then to calculate the pH, and our pH is equal to 14 minus my pH, or POH, right? Which means that I'm going to get 9.07 as my pH for our system where I added only a salt, okay? So even though this didn't look like an acid or a base, because of the fact that we added a salt that has an anion that is a conjugate base of a weak acid, that means that this acts like a base, right? So when we add it, it actually raises our pH away from our neutral 7, okay? So that's how you do a weak, or rather a salt pH problem, okay, when you have a weak component. And that covers our anions. So next, I want to talk to you about cations, right? So looking at slide 39, okay, what you're going to see is that now we're ready to talk about our 3 types of cations, all right? The first type are going to be cations that act like a weak acid. And one time where they're going to act like, or one type of cation that acts like a weak acid occurs when they pull OH minus out of solution. Okay, So if they pull OH out, all right, then they're going to act like a weak acid cation. Okay, so for what I mean by that is that if a cation is the conjugate acid of a weak base, all right. So for example, right, magnesium 2 plus is the conjugate acid of a weak base. Okay, because if I take Mg2 plus and I add 2 hydroxides, right, we would end up getting an equilibrium with magnesium hydroxide. Okay, well, magnesium hydroxide is a weak base, so that means that it is going to favor, the solid form, okay, rather than dissociating. It will dissociate a little bit, but it forms an equilibrium because it's a weak base, okay? Okay. Now, since MgOH2 forms an equilibrium, right, because it's weak, that means that Mg2 plus is capable of pulling out the OH minus and therefore acts like an acid. Okay? That means that if I had something like MgNO3, right, magnesium nitrate as a salt, right, this would be an acidic salt because it lowers the concentration of OH minus. Okay? Our second type of cation are going to be cations that are pH neutral. Okay? And they're going to be pH neutral if they completely dissociate from our OH minus. Okay? Now, when does that happen? Well, this would be like if a cation is the conjugate acid of a strong base. Right? So, for example, right, sodium plus is the conjugate base of sodium hydroxide, which is a strong base. Okay, so since sodium is the conjugate base of our since sodium plus is the conjugate acid of a strong base, that means that this will completely dissociate from OH in solution. Okay, and that means, right, that if I take sodium hydroxide, right, and I add it into water, I will get sodium plus and hydroxide ion every time. Okay? So that means that sodium is not going to be able to pull out my OH because as soon as it does, it's just going to split back up into its respective ions. Right? So, in other words, since sodium hydroxide completely dissociates then no equilibrium will form. And that means that no OH minus is pulled out. Okay, so that means that our pH doesn't change, and it would be pH neutral for that anion. All right, our last type of cation is going to be small metal cations that have a charge that is greater than or equal to 3 plus. Okay, so if they, and this would be things like aluminum 3 plus or iron 3 plus, right? If it's got a 3 or bigger positive charge, then these are going to act like a weak acid, okay? And they're going to pull OH minus out of solution, okay? So whether you have OH minus as OH minus or if you have water, these are going to be strong enough that they're going to be able to rip off an OH minus because they want to lower their overall molecular charge, okay? So let's do some examples, right? So on slide 41, right? Our first example is going to be potassium plus, okay? And we're just looking at the cations right now. If we have potassium plus, I want to know if this is basic, acidic, or neutral, Ba or N, okay? Now, potassium plus, all right? What you're going to do, as always, is going to be to dissociate your salt into ions. All right, well, I've already got the ion that I have, okay? Then you're going to take that ion and you're going to add OH minus to your cation, okay? And then your third step is going to be to say, okay, is it a weak base or a strong base? All right, if it is a weak base, okay, then that means that it will be a weak acid, okay? If it is a strong base, it will be pH neutral, okay? And if that's not satisfied, you can also ask yourself a fourth question, which is my charge greater than or equal to 3 plus? If yes, then it is acidic, okay? Now, if we're looking at potassium plus, we know that's our cation, we're going to add OH minus, and that will give me potassium hydroxide. So that is step 1, 2, or rather that's step 2, right? Because we already did step 1. Step 1 is to dissociate. That's step 2. Step 3 is to say, okay, is it a weak base or a strong base? This completely dissociates, so it's a strong. And that means that we know it is pH neutral. All right, so that's not bad. So if we were to do BAN, we would have marked it as neutral for our cation. Let's do number B, or letter B. That's going to be Cr3 plus. Okay, well, I have the anion. Let's do step 2, right? Because we'd separate it into ions. Well, I've got my cation, right? And then I would say Cr3 plus plus my hydroxides. Okay, and you're going to add however many are on the charge. Okay, so that would mean you get CrOH3. All right, well, we also know, like, so we could ask ourselves step 3, which is like strong or weak, right? We can ask ourselves that question, but we also can see right away that that has a 3+ charge. Okay, so since it has a 3+ charge, we know that it is going to be acidic. Okay. Letter C, we have another example, which is Nh4 Plus. Okay, so remember we did that example before where we said that we were looking at ammonium chloride as our salt. Okay, and we said that the chloride part was pH neutral because it completely dissociated. Now we're looking at our cation. All right, well, let's take our cation. Okay, and we're going to add OH. So I've got Nh4OH. Okay, well, my third question is weak or strong? Well, I know that it's weak. So since it is weak, okay, that means that it is going to be acidic. Okay, so I had that the ammonium was acidic, and I had that my chloride was neutral. Okay, so at this point, right away, I know that this is going to form an acidic salt. Okay, now, if one of them is neutral, right, whether it's the anion or the cation, then that means that whatever the other species is, if one is neutral, then the other one wins. Okay, so if the other one were basic, then that means that the salt's going to be basic. If the other one were acidic, that means the salt's going to be acidic. All right? Now, what if we have one that's acidic and one that's basic? I will talk about that when we get to a more complicated example. All right? Now, so we talked about our anions and our cations. Okay? So in our next video, I'm going to walk you through how to put them all together like we did in that last example to go through some more examples of the salts as a whole.